To discuss the concept of molarity, which is something we've seen a little bit here and there as we've been going through this year. Discuss what molarity it is, and then we're going to discuss how to use it, both in terms of calculations and how to make solutions of known molarity or known concentration as we head towards our next lesson, which is going to be stoichiometry using molarity, and next week's lab, which is making up solutions of known concentrations and then using a special technique for verifying that we have the correct solution. So molarity is a measure of the concentration of a solution. So we saw concentrations yesterday, but the concentration units we saw yesterday aren't useful to us if we want to measure out a known amount of a solution to get a known quantity of the solute. So what molarity tells us is how many moles of solute we have in exactly 1 liter of solution. So if you know the volume of the solution you measure out, you should be able to determine the number of moles of the solute, and that's helpful. That is helpful in stoichiometry and just knowing how much solute you have in the solution. So on your reference pack, you will see that molarity is defined as moles per liter or moles per volume, and both of these equations show this. Molarity, moles of solute divided by 1 liter of solution. Capital M is the abbreviation for molarity. You must use that capital M. And I'm going to introduce something here that I usually don't introduce quite so early, but we might see it. Another way of writing molarity is if we write some chemical in square brackets. That also indicates the molarity of whatever X is in the square brackets. And we'll be using this abbreviation soon enough. So really simple calculations here. If we have 1 mole of hydrochloric acid in 1 liter of solution, then we have a 1 molar, that's how you pronounce it, 1 molar, just like the tooth, 1 molar solution of hydrochloric acid. If we have 2 moles of sodium chloride in 1 liter of solution, then we have a 2 molar solution. And this is a tricky calculation here. I'm being silly. 1 mole of sodium chloride in half a liter of solution. You can think of this as, suppose you had a full liter, you'd have twice that amount. And so this would be 2 molar solution of sodium chloride. So let's put some more realistic numbers on these. If you have 3.0 moles of copper 2 sulfate in 4 liters of solution, what is its molarity? So we take the 3.0 moles divided by the 4.0 liters of solution, and that gives us 0.75 molar solution. So essentially, if we took 1/4 of that 1 liter of that solution, we'd have exactly 0.75 moles of copper 2 sulfate. Now, suppose we add 3 moles of KCl in 500 milliliters. Watch that. This is a conversion alert. The volume for molarity must be in liters. So the first thing we're going to do is take that 500 milliliters, and I'm going to put a decimal point there for some precision. 500 milliliters, and we have 1 liter in 1,000 milliliters, and that gives us 0.500 liters of solution. And then the molarity is just that 3.0 moles divided by 0.500 liters, or 6.0 molar solution. So nothing tricky about that. Now, suppose we put 4 grams of hydrochloric acid of HCl into 250 milliliters of solution. What is the molarity? First thing you got to do is find the moles. Frequently, what people forget to do is to convert from grams to moles. I tell them this is not a grammarity, it's a molarity. So moles of HCl, I'll spot you the molar mass of HCl, 4.0 grams times 1 mole over 36.5 grams. And that gives us 0.11 moles of HCl to sig figs. And then molarity, the concentration, is just equal to 0.11 moles divided by, let's do a little conversion, a quick conversion. 250 milliliters becomes 0.25 liters, so 0.25 liters, and that comes out to be 0.44 molar solution. All right, finally, let's turn this around, and this is where the usefulness in molarity comes in. Suppose I wanted to know how many moles of aluminum chloride I have in 100 milliliters of 5 molar AlCl3 solution. And so there's a couple of ways you can solve this. You can rearrange the molarity equation and take molarity is equal to moles divided by volume and rearrange that to find that the number of moles is equal to m times v. As long as your volume is in liters, then we're good to go. The other thing you can do is you can solve this using dimensional analysis. So suppose I want to know how many moles of AlCl3 I have. Start with the volume. Why the volume? Because the molarity is actually a conversion factor. If we look and see how the molarity works, this molarity is a conversion factor between volume and moles. And so I'm going to start with my volume, which is the single unit, and again, convert that to liters, and let's put a decimal point there for precision. No, I didn't do that on the 250. Let's do that on the 250. Doesn't really matter there. And we have 0.100 liters times, and the molarity was 5.0. Now we can split apart that unit, moles per 1 liter, and you see that the liters cancel out, and that's going to give us 0.50 moles of AlCl3. And it would work the same way if you plugged in up there. If you plugged that in up there, we'd have the exact same answer. So you can try that just to be sure. Either way is acceptable to me, and the notes that you'll see, the pre-filled in notes, have the solution, have the answer solved that way. All right, the only thing I haven't done here is asked you about finding the volume if you know the concentration and the number of moles, and we can talk about that. I think it's one of the homework problems where you can talk about that when we next meet. So making these precise molar solutions requires a very precise device to measure out the volume of the solution. Now, I want you to remember, you're not measuring out the volume of the liquid going into the solution. I'll be stressing that both here and later on. We're going to measure the volume of the final solution that we make up. To do that, we're going to use something called a volumetric flask. And volumetric flasks are very precise flasks, very precise pieces of glass, or there's some plastic ones as well, that come in various sizes. And we have a whole slew of them ranging from 25 milliliters all the way up to some 2-liter flasks. And I'm going to insert here another video that I took earlier that just shows an array of the volumetric flasks and what they look like. This is a set of volumetric flasks ranging in size from 25 milliliters at the small end all the way up to 2,000 milliliters or 2 liters at the large end. Typically, to make up solutions for labs, we would use the larger 1,000 or 2,000 milliliter flasks to make up the main solutions for your labs. In the lab that you would have been doing for this particular unit, we would have used the 25 milliliter and 50 milliliter volumetric flasks down at this end. All volumetric flasks have a large large capacity at the bottom that will hold most of the liquid, a narrow neck coming up to a calibration line, and that narrow neck is to enable precise amount of liquid to be put in so that the amount of liquid in the flask is exactly what's listed on the size of the flask, and the stopper up at the top to allow you to invert and shake the stopper or shake this flask so that you can mix the solution properly. So you've seen a volumetric flask now, and let's see how we're going to use those volumetric flasks and how we're going to make these precise solutions. There is a process, a couple of steps involved. We're going to see these steps in the lab that we do next week, and I'm going to ask you in the homework, and eventually if we have a test on this, to fill in, to describe the steps as you go through. So I want you to take some solid NaCl. So the first solutions we're going to make are going to start with the solid solute. And I want you to dissolve it in the right amount of water, take the right amount of NaCl into the right amount of water to make 500, and let's again put a decimal point there for precision, milliliters of 3.0 molar NaCl solution. So step by step, the first thing we're going to have to do is we're going to have to figure out how many grams we need. Unfortunately, our balances don't yet read out in moles, so we're going to find moles. Now, remember up above, we had the moles of NaCl is going to start with the 0.500 liters, and we're going to multiply by that 3.0 moles divided by 1 liter. By the way, that 1 there is not significant. It's infinite significance because it's exactly 1 liter. And so we are going to need to measure out 1.5 to 2 sig figs moles of NaCl. Next step is to convert the moles of NaCl to grams of NaCl. So take that number, and we're going to multiply that by the molar mass. Again, I'll spot that for you because I'm sure you can determine the molar mass. 58.44 grams of NaCl over 1 mole of NaCl. And that's going to give us 87, not decimal yet, 87.7 grams of NaCl. So what you would do is go to a balance in the lab and measure out 87.7 grams of sodium chloride. So step by step, the first step is mass out the 87.7 grams of sodium chloride and put that into a 500 milliliter. I put a decimal there. You don't really need it because 500 milliliter flask is precise. Milliliter volumetric flask. Okay, next part is you're going to fill the flask about 3/4 full. Now that's 3/4 of the way up to the shoulder. Don't go up into the neck yet. 3/4 of the way full with your solvent. In this case, it is water. You're going to stopper it. You don't want anything splashing out. And shake / agitate until your solute is all dissolved. Okay, next you're going to fill the flask to the 500 milliliter line. So remember seeing those lines, the 500 milliliter line with your solvent. And you're going to use a dropper to get exactly 500 milliliters. And as you'll see in the lab, we're then going to stopper and shake some more to thoroughly mix. And finally, you're going to have to do a little check. Check the level of the solution. You may need to top it up. So if needed, fill to the line again and mix. And the reason for this is as you dissolve or as you dilute the solution, what you're going to find is that the volume, the mixing volume, is actually going to be slightly less, and so it might go down in volume. If you remember back to our density lab, when we mixed the 10 milliliters of methanol with 10 milliliters of water and ended up with 19 milliliters, not 20 milliliters of solution, that was the same thing. The solute fits within the in between the molecules of water and can decrease the volume. So finally, we now have a 500 milliliters. We'll have 500 milliliters of the 3.0 molar NaCl solution, and we're done. So that's what to do if you have a solid solute. We don't always have solid solutes. Sometimes we have something already dissolved, and that concentrated solution is called a stock solution. And I have a whole bunch of these stock solutions, especially acids, concentrated acids. And we'll talk about acids in a little bit. They sometimes are needed because the solute is difficult to dissolve, or sometimes in the case of the acids, the solutes are actually gases, and so it makes it difficult to transport. So these guys are going to be things that we're going to find in our stock room. So for instance, we have 12 molar hydrochloric acid. That is the concentration of the hydrochloric acid in the big bottles that I've shown you. So 12 molar hydrochloric acid. By the way, you can find hydrochloric acid, this 12 molar hydrochloric acid, in any hardware store. It goes under the name muriatic acid. That was the old name for it. And it's used for things like cleaning concrete and general cleaning up of things. Be very careful if you use it, though. It does fume. And you also find this at pools, used to help keep the pH of the pools from going too basic. So what we want to do is dilute this 12 molar HCl down to only 3 molar HCl. And we want to make 250 milliliters of this HCl solution. And so one of the things you want to do is organize your data. You want to keep that data together and figure out what you need and what you have. So one of the things we're going to realize is that as you take the concentrated solution with a smaller volume, we're going to add solvent. When you add solvent, the volume is going to get greater because you've added that solvent, and so the solution is going to get more dilute. What you haven't changed is the amount of solute is constant, right? All you've added is your solvent. So that's going to help us to understand what to do here. So there's two ways of doing this, and either way works. The second way I'll show you is easier, but the first way breaks it down into its steps. The first thing you do is calculate the moles of HCl that you need in the dilute solution. So our dilute solution was the moles of HCl was our 250 milliliters, or 0.250 liters of 3.0 moles per liter, and that equals 0.75 moles of HCl. Now we're going to take that 0.75 moles of HCl, and now here's where the volume comes in. We can take that 0.75 moles of HCl, and you can put it into the equation and rearrange to solve for, so if we start with molarity, is equal to moles over volume. Remember the trick, switching across the diagonal will give us that the volume is equal to the moles over the molarity. Or dimensional analysis, take that 0.75 moles of HCl. Now here's where the conversion factor comes in handy. We have moles, we want the volume, so we're going to multiply that by 1 liter over 12, not molar, let's put the moles there, 12 moles. So now the moles are going to cancel out and they're going to leave us with the liters, and either way should get us the correct answer of 0.0625 liters, or multiplying that by 1,000 milliliters over 1 liter gives us 62.5 milliliters of our concentrated solution. So notice as the molarity went down, so go back over here. The molarity over here went down. The volume we needed, the volume that we got, back over here, the volume that we got went up. Over here, the molarity was higher, and so the volume was lower. And this is an inverse relationship, which we have seen before. The other way of doing this, and this is another equation that's on your reference charts, is to, as I said, remember that the moles of each are equal. All the way over here. And since moles is equal to molarity times volume, we're just going to set the moles of the concentrated solution times its volume equal to the moles of the dilute solution times its volume as well. And the equation on the reference chart lists this as M1V1 equal to M2V2. And again, remember, this is an inverse relationship because they're equal to a constant. As the molarity goes down in the second equation, the volume is going to go up. I've already given it away to you what type of relationship this is. Now, the cool thing about this is you don't need to convert to liters, because what's going to end up happening is that the milliliters will either cancel out in the end, or they will be the volume that you're ending up with at the end. So let's plug in the numbers. Actually, before we plug in the numbers, let's rearrange the equation. So we're looking for the volume of the concentrated solution. This is what we want to know, how many milliliters we need. So the volume of the concentrated, CONC stands for concentrated, is going to equal the molarity of the dilute solution divided by the molarity of the concentrated solution times the volume of the dilute solution that you want. And so that's going to be 3.0 molar divided by 12.0 molar times the concentrate times the volume, which was 250 milliliters. Notice the molarities cancel that. They leave us with milliliters. Now, if you wanted to use liters there, you could. And it doesn't matter which way you do it. But if you do convert to liters, don't forget to convert back to milliliters. I will probably ask you to give me the answer in milliliters. Also, make sure you do the conversion correctly. 250 milliliters is not 250,000 liters. It's 0.250 liters. Make sure you go in the right direction. All right, so we cancel things out. This is going to be 1/4 of 250 milliliters, or as we saw up above, 62.5 milliliters of solution. That's the 12 molar HCl. So that's how much you need. Now, making these solutions can be a little tricky. The first thing is measuring out the amount of the concentrated solution you need. So Measure 62.5 milliliters of that 12 molar HCl precisely. And in the lab, we're going to see a way to measure it precisely. And then you want to put it into that 250 milliliter volumetric flask. But there's a trick that we have to follow with acids. This is only with acids. This flask already let's say already half full with water. So down here, the safety note. With acids, we always add concentrated acid to water. We add acid to water, do as you oughter, because if you don't do that, if you add water to acid, it's a very exothermic reaction, and it could splatter. And if you splatter, it could get acid out of the volumetric flask, or acid splattering onto you. All other solutions, it's okay to add water to the concentrated solution. Be careful when you're adding acid to water. Be sure, watch your volumes. Make sure you have enough room for the concentrated solution. In other words, don't overfill the volumetric flask. Make sure you leave room, a little margin of error in there so you don't overfill the flask. Keeping in mind, you probably will get a reduction in volume, but you don't want to have, say, 50% full. You don't want to have to be half full if you need to put in, say, 3/4 full of your concentrated acid. After this, it's pretty easy. Whether you started with half full or whether you started with it as it is now, we're going to swirl it to mix. And then fill. You can stop it, but generally you don't have to. Then you fill to the 250 milliliter line with the dropper. And you'll see again how this works when we see the video for the lab. The dropper, that gets you exactly to the line. And finally, as before, stopper and mix thoroughly. And don't forget to double check and top it off if needed, just like before. All right, so this is all we need to know about making Molar Solutions, and it's time to go apply this. So go do the homework, and we will talk about this at your next meeting.